Hello, my dear students, and welcome back. I know. The board exams are just around the corner, and sometimes this electricity chapter can feel a bit, well, shocking. But please don't worry. In the next few minutes, we are going to make this chapter so simple, you'll feel like a real expert. Look, I get it. All these formulas and concepts, they can feel like a big jumble in your head. But trust me, once we break them down piece by piece, you'll see how logical and honestly, how easy it all is. Are you ready? Chalo, let's begin. So here's our little game plan, our roadmap to mastering this chapter. We'll start with the absolute basics, current and circuits. Then we'll understand the push, that is voltage, and the golden rule, Ohm's law. After that, we'll tackle resistance, see how resistors work together as a team, and finally, we'll look at how all this electricity actually works in our daily lives. Okay, first things first, what even is electricity? Well, at its heart, it's just a flow of energy, and the easiest way to picture electric current is just to imagine water flowing at a river. Simple, right? Let's dive a little deeper. So, inside a metal wire, instead of water, we have these tiny electric charges called electrons, and they are the ones flowing. So electric current is nothing but a measure of how many of these charges flow past one point every single second. And we measure this flow in the unit called amperes, or just A for short. And here is our very first key formula. It looks simple, and it is simple. I stands for current, Q is for the amount of charge, and T is for time. So current is simply the total charge that flows divided by the time it takes. I equals Q by T. Please remember this one. Now, for these charges to actually flow, they need a complete closed path, kind of like a racetrack. We call this path an electric circuit. As you can see in this lovely diagram, a simple circuit needs a power source, like a battery, some wires to make the path, something to power, like a bulb, and of course a switch to open or close the track. If the path is broken anywhere, the flow just stops. But what makes these charges move in the first place? They don't just decide to run on their own. There has to be some kind of a push, doesn't there? Well, that brings us to our next super important topic. This push is called potential difference, but you and I know it by its more common name, voltage. Think of a water slide at a park. For the water to flow down, the slide needs to be high up, right? Voltage is exactly like that. It's the electrical slope, or pressure, that pushes the charges forward, and we measure it in volts, or B. Now, here's where things get really interesting. There is a beautiful relationship between this push, the voltage, and the flow, the current. A brilliant scientist named George Simon Ohm discovered a law that connects them, and I'm not kidding, it is probably the most important law in this entire chapter. And this is the golden rule, my students. V equals I times R. That's the law in one simple, powerful formula. Voltage equals current multiplied by resistance. If you just remember this one triangle, you can solve so many problems. V, I, and R, they are the three best friends in electricity. But wait a minute, who is this new friend R? We talked about the flow, and we talked about the push. Well, R, or resistance, is the opposition to the flow. It's like having speed breakers on a road. It creates a sort of traffic jam for our little electrons. So, what causes this traffic jam? Well, four main things, right here on your screen. First, the length of the wire. The longer the road, the more resistance. Makes sense, right? Second, the thickness. A wider, thicker road lets traffic flow easily, so less resistance. Third, the material itself. Copper is like a smooth expressway, but other materials can be like bumpy village roads. And finally, temperature also affects it. Let's think about this with a real-life example. This is a very common exam question, by the way. We want our toasters and geysers to get really hot. So why don't we use something like copper, which is a great conductor? Why do we use something called an alloy, like nichrome? And here is the secret. Alloys are basically champions when it comes to resisting current. They have a very high natural resistance, which means they create a huge traffic jam for the electrons. All that struggle and friction generates a lot of heat. Plus, as you can see, they have a high melting point and they don't burn out easily. Absolutely perfect for a toaster. You know, in any real circuit, like the wiring in our homes or those beautiful Diwali lights you see, we almost never have just one thing. We have many resistors, all working together as a team. And they can be connected in two main ways. Let's see how this teamwork happens. Okay, beta, this slide is super, super important, so please pay close attention. In a series connection, everything is connected one after the other in a single line. The most important thing to remember here is that the current stays the same for everyone. But in a parallel connection, they are in different branches, so the current gets divided into different paths, but the voltage is the same for everyone. You should definitely memorize this table. Just look at this simple drawing. It makes it so clear. On the left, you see a series connection. It's just one single path for the current to follow. But on the right, we have a parallel connection. See how the current reaches a point and then splits up to go through different paths? The difference is very clear, isn't it? Okay, it is time for our special exam corner. This is a typical question you might find in your exam paper. Let's solve it together, right now. We have a lamp and a conductor connected one after another. The key word is in series, with a 6-volt battery. We need to find the total resistance and the current. Okay, step 1, it's a series circuit. That means to get the total resistance, we just add them up. So 20 plus 4 equals 24 ohms. Simple. Now for step 2, we bring back our golden rule, Ohm's law. We know V equals IR, so I equals V by R. The voltage is 6 volts. The total resistance is 24 ohms. So 6 divided by 24 gives us 0.25 amps. See? So easy. Shabash. Well done. Fantastic. We are almost at the finish line. For our last section, let's just quickly look at the effects of electricity that we see and use every single day. When electricity flows, it creates heat, and our devices consume something called power. Have you ever wondered why your phone charger or your laptop gets warm when you use it? Well, that's because of the heating effect of current, and it's described perfectly by Joule's law. The heat produced, H, is equal to the square of the current times the resistance times the time. That I squared is why things with high resistance, like our water heaters, get so hot so fast. And what about power? You've all seen watts written on your LED bulbs or phone chargers, right? Well, power is just how fast an appliance uses up electrical energy. The more the power, the more energy it eats every second. And the most basic formula for it is simply power P equals voltage V times current I. And to wrap it all up, here they are, the 5-star must-remember formulas for this chapter. Please take a screenshot of this slide. This is your key to scoring full marks on any question from electricity. You have V equals IR, the series and parallel formulas, heating, and power. That's it. That's the whole chapter in one slide. And we're done. We've revised the whole chapter. See? It wasn't so scary after all, was it? I really hope this quick revision has charged you up with confidence for your exams. If there's any part, any formula, or any concept that you still find a little difficult, just let me know in the comments below. I read every single one, and I will try my best to help you out. Don't forget to like this explainer, share it with all your friends, and subscribe for more chapters. All the very best.